We'll proceed in Taylor multivariable series, Taylor polynomial approximation for the multivariate. Taylor series, you are really amazing, you are really marvelous. So, Taylor series is something that has kind of changed the calculus world, where you don't find any what I would say, if you don't find any excuse, if you don't find any leeway, if you don't find any path, then think about Mr. Taylor series, because you know that any function fx can be represented using set of polynomial algebraic equation, that is Taylor series, and then you have kind of some kind of what I means easy life when you have something that represented as kind of a polynomial equation, then you have some easy life. Okay, so we have seen Taylor series in three ways how to prove the Taylor series. Then we saw that how Taylor series would work when it is multivariable case. So single variable case and multivariable case. Taylor series are respite in when you are in contingency. So that is the Taylor series. Now in multivariable case, what we saw in, we will revisit the multivariable case. Then we will go more in multivariable case. So the single variable case for the Taylor series, if you see the single variable case for the Taylor series, then it is if there is any function fx, then it can be represented using gx, where gx equal to fa, where x equal to a at any point a, fa plus dfx by dx, where x is a into x divided by factorial of 1, plus d2fx by dx square at x equal to a into x minus a. Okay, there dfx, I'll start again, gx equal to fa. F is a function and gx is a replica of function fx as gx, but fx can be anything: polynomial, algebraic polynomial, trigonometric, logarithmic, exponential, and so many things. Fx, gx, but gx is only polynomial. Now what gx is? Gx equal to fa, f at a plus dfx by dx at x equal to a into x minus a divided by factorial of 1, plus d2fx by dx square at x equal to a x minus a whole square divided by factorial of 2, plus d3fx by dx cube x minus a into at d3fx by dx cube at x equal to a x minus a to the power 3 divided by factorial of 3, plus and so plus at the end dn fx by dxn at x equal to a x minus a to the power n divided by factorial of n. So this is called Taylor approximation for any, that is gx, for any function fx. What about the multivariable case? Multivariable case, we have seen for multivariable case, if this is xy plane, this is xy plane, this is x-axis, this is y-axis, this is fxy or z-axis. If this is xy plane, then I have a 3D surface that sits at the xy plane. If it sits at the xy plane, then at any x comma y, any point on the xy plane, what is z? When full surface is sitting at xy plane, then z is 0. Everywhere z is 0. Now this is y-axis and this is x-axis. Now I am tilting it like this. Now what is z? This is xy plane. If this is xy plane, there is any point x comma y. If there is any point x comma, this is origin now. This is origin, this is x-axis, this is y-axis. If that is the case, If that is the case, then at any point x comma y, what is z? Z is nothing but what is dz by dx. If it is tilted like this, if this is x-axis and this is z, then there is dz by dx, dz by dx, if this is z. Whatever the slope is, and if I want, this is xy plane. At this, that is x comma y. And for this x, what is z? dz by dx into x. What is y? dz by dy into y. There is no dz by dy because y is like this only. Now keep this x-axis constant. Earlier I kept y-axis constant and tilted the x. Now if I want at any point x comma y, what is z? That is nothing but dz by dx into x. Okay. Now tilt it, keeping x-axis constant, and tilt like this. Now same point. Okay, or I would rather say keep this x-axis like this and tilt like this. Can you see this? This point was earlier down. Now this point is coming up. Now what if now this is xy plane. It is very near now. So what is at any point x comma y? What is z? That is dz by dx into x plus. Now earlier it was like this. When I tilted like this, then there is a dz by dy also, because keeping x constant and tilting y now. So then dz by, so whatever down it is through. Now this is the slope for the x-axis. Now keeping the x-axis constant, if I make this like this, full rotate if like this, then it is showing slope along y-axis. If I keep like this and only rotate along keeping x constant, then I can rotate along y-axis. Keeping y constant, I can rotate along x-axis. So first I rotated along x-axis. Earlier this is xy plane and surface was at xy plane. So every xy, the height fxy is 0. If that is the case, now if I tilt like this, then at any x comma y, what is the z? Now there is z, that is negative. If that is the case, then it is dz by dx into x. Now if I move like this, then it is coming up. It is less, it is high, it is less. If this case, then there is a dz by dy now. So what is net z? So dz by dx into x plus dz by dy. So if slope is like this along x-axis, then z is down. But if I moved like this, then z is coming up. How much up it came? That is dz by dy into y. So dz by dx into x plus dz by dy into y. So that is the fxy. So fxy equal to dz by dx into x plus dz by dy into y. And this is the crucial if we want the derivation of the product, that we go through chain rule, or chain rule is the integration. This is the place where it starts from, because there are two axes x and y, and this is how we proceed. So if that is the case, then gxy, if I say fx, what is polynomial? If I have a polynomial equation, if I have a algebraic equation fxy, algebraic equation fxy. So say it is of leave it. So there is a function fxy, there is a function fxy. I don't know what is the function. Now for this function, the approximation, Taylor approximation gxy, I know. Gxy for the first order derivative is dz by dx into x plus dz by dy into y, or gxy equal to dfxy by dx into x plus dfxy by dy into y. If this is gxy, then what is the original function fx? For which, so from fx, if I want to create the copy of fx as gx, then I need single derivative. That's why it is single derivative, dfxy by dx into x plus dfxy by dy into y. So this proves that fxy is x plus y. If fxy equal to x plus y, then it is asked, because because the equation what it is forming is dfxy by dx, dfxy by dy. So it is asking for dfxy by dx and dfxy by dy, because gxy, when it is creating mirror copy of fxy, it needs that. If it needs that, then what if fxy equal to x plus y, what it would send? It would send dfxy as 1, dfxy as 1, and dfxy by dx as 1, dfxy by dy as 1, that is x plus 1. Okay, so for that, this is the carbon copy. So carbon copy of function fxy equal to x plus y. If it is x plus y, if it is x plus y, then dfxy by dx and dfxy by dy, we can provide, nothing else is required. Anyway, if I am making exact copy, if fx is a function for which gxy is an exact copy, fxy is a function for which gxy is an exact copy. If that is the case, then if exact copy is dfxy by dx into x plus dfxy by dy into y, if this is the exact copy, consider the single dimensional. We are talking about multivariable, single variable. If gx equal to dfxy by dx into x, if this is the carbon copy, then what is the original function? Then original function is x, just x, because if I do dy by dx of x, it becomes 1. If I do dy by dx, it becomes 1. That dy by dx, if I supply here 1, then the equation as a copy, we know that line equation, any line equation is nothing but gx equal to dfxy by dx into x. If dfxy by dx is 1, then 1 into x, that is x. Here also x, here also x. Both are exact copy. Similar fashion, if I have gxy equal to, that is what we calculated now. That is what we calculated now. So, if gxy equal to dfxy by dx into x plus dfxy by dy into y and dfxy by dx and dfxy by dy, if both are 1 and 1, then it is x plus y. If that is the case, then if it is exact replica of fxy, then fxy is x plus y. Same way, if gxy, that is exact replica of fxy, and gxy equal to dfxy by dx into x plus dfxy by dy into y, and both dy by dx and dy by dy are 1 1, then it resolves to x plus 1. If that is true, then if gxy is exact replica of fxy, then fxy is nothing but x plus y. Here x plus y, then here also x plus y. Now let's try the dfxy by dx and dfxy by dy for the fxy. If I calculate dfxy by dx, then y term gone, it is 1. If I calculate dfxy by dy, dfxy by dx 1, dfxy by dy, then x is gone and it is 1 again. If 1 1, if I give this, and it has formula dfxy by dx into x plus dfxy by dy into y, if it replaces with 1 and 1, x plus y is exact copy of x plus y. Now, for the single variable case, if fx is x, then exact copy in gx is x. Gx is x. Here, exact copy of x plus y, then here exact copy is x plus y. This proves that. Now we come to multivariable case. If I have a surface, consider this is xy plane. If this is xy plane, if this is xy plane, then this is z axis. This is fxy. If this is xy plane, this is fxy. Fxy means fxy, f small f in braces x comma y. If that is the case, this proves that this is algebraic function over independent variable x comma y. Small f in braces in function bracket x and bracket close. Function over independent variable x. f x comma y, function over independent variable x and y. No, this is function over independent variable x, y plane. This is another way. This here the difficult research is required. That if it is fxy, fx comma y, the independent component is not x-axis and y-axis. Independent component is x plus y. I mean, sorry, xy plane. That is only one independent component, xy plane. If xy plane is independent component, then dependent component is f braces x comma y brace close. If that is the case, then if I have fxy equal to x plus y, then gxy equal to dy by dfxy by dxx plus dfxy by dyy, where both are 1. If this is exact replica of fx equal to x, and here gx equal to dfx by dxx, this proves that if it is a single case, then x is an independent variable. Then if it is multivariable case, then x plus y is the independent variable. So we are talking about, don't, in multivariable case, don't keep more than one independent variable. That is the struggle that is going on. If there is only one independent component in multivariable case, that is x comma y, then independent component is xy plane. This is what I am trying to say. If it is xy plane, if it is xy plane, if it is xy plane, then if it is xy plane, then xy plane is x plus y. If that is the case, then fxy and gxy, fxy and gxy. So if I kind of if I try to, if I have a polynomial equation, okay, so if I have polynomial equation, that is x square, early in single variable case it is. Now how we proved the Taylor series? So we took polynomial fx as series of polynomial equation. So if it is a series of polynomial equation, then it is fx equal to fa, where it is at a fa plus x minus a plus x minus a whole square plus x minus a to the power 3 plus x minus a to the power n. Now for this function, if I want Taylor series, then 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 now this is fx and this is gx. Gx wants first zero order derivative. Zero order derivative. If it is zero order derivative, then fx equal to fa plus x minus a. Now let's substitute x with a. If you substitute x with a, all becomes 0 except the first one, that is fa. That is zero order derivative. It returns fa. Now gx equal to fa. Now it is asking for first order derivative. So first order derivative is fa gone. Now x minus a, first order derivative is 1. It returns 1. Then it becomes now fa plus dfxy by dx at x equal to a, x minus a. This is what now I am replicating. Now second order derivative. So first order when we derivative, when we called, we did the first time derivation, then fa gone, x minus a become 1, and other, when x equal to a, all becomes 0. So 1 is returned. Now second order derivative. Second order derivative, fa gone, x minus a gone, x minus a to the power 2. Second order derivative is 2. Others at x equal to a, all become 0. So it is returning 2. If that is the case, now gx equal to fa plus dfx by dx x minus a plus, now 2 is written, d2fxy by dx square at x equal to a, x minus a whole square divided by 2, because 2 would null it. Now third order derivative, fa gone, x minus a gone. If you do triple derivative, x minus a whole square gone, x minus a to the power 3 becomes 3 into 2 into 1. Other, x minus a to the power 4 other at x equal to a, all become 0. So 3 into 2 into 1 is returned. Now gx equal to, that is the polynomial approximation of fx, gx equal to fa plus dfxy by dx x equal to a x minus a plus d2fxy by dx square x at a x minus a whole square by 2 plus now 3 into 2 into 1 is written plus d3fxy by dx cube at x equal to, when x equal to a x minus a to the power 3 by factorial of 3. This is how it will keep on going till it becomes dn fxy by dxn at x equal to a x minus a to the power n divided by n factorial. Now x. Now leave x minus a. Just leave it x only for simplicity. So fx equal to fa plus x square plus x to the power 3 plus x to the power 4 like this. X is replaced with x plus y. Now fxy, earlier it is fxy equal to fa. Now it is fa comma b. fa comma b. Earlier now it is fa comma b. fxy equal to fa comma b plus x plus y plus in bracket x plus y whole square, because x-axis is replaced with xy plane number. This is our proof. This is not available anywhere else, and it is the simplest proof. Just go and see how in some way people are proving it that they only understand. Now replace all x with x plus y. If that is the case, then zero order derivative is gxy equal to fa comma b. Single order derivative, zero order derivative. First order derivative, that is x plus y, is dfxy by dx1, dfxy by dy1. That is given here, 1, 1. Okay. Now it becomes dfxy by fa comma b plus dfxy by dx into x plus dfxy by dy into y divided by 1. Now second order derivative, that is x plus y whole square. If it is x plus y whole square, then it becomes x square plus 2xy plus y square. If that is the case, then d2fxy by dx x square is 2. d2fxy by dy square is 2, and 2xy dfxy by dx into dfxy by dy equal to 2. But this 2 is anyway available, whereas x square and y square 2 came from nowhere, because x square coefficient is 1. X plus y whole square becomes x square plus y square plus 2xy. X square coefficient is none, y square coefficient is none, 2xy, for xy coefficient is 2. If I say d2fx by dx square, then 2 coefficient comes. d2fx by dy square, then 2 coefficient comes, because x square, if you do dual derivative, it becomes 2. Y square, if you do dual derivative, it becomes 2. 2xy. Okay, x square plus 2xy plus y square. If I do dual partial derivative along x-axis, 2xy and y square both become 0. If I do dual derivative along partial derivative on y-axis, then x square plus 2xy becomes 0. If I do single derivative dfxy by dx, then x square becomes 2x plus 2y plus 2y again. Now if I do, okay, sorry, y square gone. If I do partial derivative along x-axis, then x square becomes 2x and 2xy becomes 2y. If I do plus y square gone. If I do partial derivative along y-axis, then 2x gone. 2y becomes 2. Okay, so all about x square plus 2xy plus y square, or x plus y whole square, that there are three partial derivatives: dfxy by d2fxy by dx square, d2fxy by dy square, and dfxy by dfxy by dy. If I send here, then this becomes d2fxy by dx square into x square divided by factorial of 2 plus dfxy by dx into dfxy by dy. Nothing division is required, because same 2 is coming, plus dfxy by dy d2fxy by dy square into y square by factorial of 2. Okay, let's go to third derivative, that is x plus y to the power 3. What is fxy? Fxy is nothing but equal to fab, f bracket a comma b, plus x plus y in bracket plus in bracket x plus y whole square plus x plus y to the power 3 plus x plus y to the power 4 plus x plus y to the power n. So if that is the case, then third derivative, if we want, x plus y to the power 3, that is the third derivative. If that is the third equation. X plus y to the power 3, that is nothing but x plus y into x plus y to the whole square. X plus y into x plus y whole square. So if I see, then it becomes x square plus 2xy plus y square into x plus y. That becomes x to the power 3 plus 2x square y, 2x square y plus 2y square x. Now if I multiply by y, then it becomes x square y plus 2 2x y square plus y to the power 3. I believe it will become x to the power 3 plus 3x square y plus 3y square x, or 3xy square plus y to the power 3. Now, if I want triple derivative, then there are four derivatives that is coming into the picture. One is d3. Why four derivative is? Now consider that it is, instead of x, it is x minus a. Instead of y, it is y minus b, the way we did in single variable. So x minus a, y minus b. If I go for triple derivative, then other variable, that will be x plus y to y whole square, or rather I say x minus a plus y minus b to the power 4. Those terms, if I do triple derivative, those terms will remain as x minus a and y minus b. When x equal to a and y equal to b, then all will become 0. So if that is the case, then this term x minus a plus y minus b to the power 3, this term full, it has to be exhausted. Then only it will not become 0 when x equal to a and y equal to b. Same as single variable we had taken. Now we have x to the, now minus a and minus b I'll remove now. So x to the power 3 plus 3x square y plus 3xy square plus y to the power 3. If I do triple derivative d3fxy by dx cube, then only x to the power 3 will remain, that is 3 into 2 into 1. d3fxy by dy cube, then only y to the power 3 will remain, that is 3 into 2 into 1. d2fxy by dx square into dfxy by dy, if I do, then only 3x square y will remain, that is 2. Okay, now if I do dfxy by dx into d2fxy by dy square, then only 3xy square will remain, other will become 0, that is nothing but 2 again. Now if I replace this third order derivative here, then gxy becomes fab plus dfxy by dx into x divided by factorial of 1 plus dfxy by dy into y divided by factorial of 1 plus d2fxy by dx square into x square divided by factorial of 2 plus dfxy by dx into dfxy by dy plus d2fxy by dy square into y square divided by factorial of 2 plus now d3fxy by dx cube into x to the power 3 divided by factorial of 3. Here are, before that it was factorial of 2 divided by, plus d2fxy by dx square divided by factorial of 2 into dfxy by dy plus dfxy by dx into dfxy by d2fxy by dy square by divided by factorial of 2. plus d3 fxy by d3 fxy by dy cube into y to the power 3 divided by factorial of 3. Please keep doing like this. Okay. If that is the case, at the end gxy equal to fa comma b plus dfxy by dx at x equal to a, x minus a plus dfxy by dy at y equal to b into y minus b. Now you have to replace all x and y with x minus a and y minus b. This is multivariable case of the Taylor series. Okay, this proof is our proof and we will file disclosure. So there is a heavy research going on here that can be considered the x-axis and y-axis in multivariable case rather than two different axes can we consider it as single independent variable, that is xy plane. So instead of x-axis and y-axis, this is multivariable. Consider xy plane as single independent variable. Now let's try with another one. fxy. Now this is two variable. Now third variable fxyz. There is a density function, that is fxyz. What is equivalent in gxyz? fxyz gxyz. If that is the case, then fxyz, the way we took x-axis as independent component in single variable, double variable xy plane as constant as independent variable. Now in triple variable case, we'll take a cube xyz cube as independent variable. If that is the case, then all x was replaced by x plus y. Now all x will be replaced by x plus y plus z. Now fxy equal to fabc plus x plus y plus z plus x plus y plus z whole square plus x plus y plus z to the power 3. See how nice it is. Now this way it will keep on going. Now zero order derivative, then gxyz equal to fabc plus first order derivative, then dfxyz by dx into x divided by factorial of 1 plus dfxyz by dy into y divided by factorial of 1 plus dfxyz by dz into z divided by factorial of 1. Now, second order derivative, that is x plus y plus z whole square. That is nothing but x plus y in one bracket plus z whole square. That is nothing but x plus y whole square plus z square plus 2x plus y in braces into z. Now x plus y whole square becomes x square plus y square plus 2xy plus z square. Now plus 2xz plus 2x 2yz full. Now how many partial derivatives are required? One is dfxyz by dx, d2fxy by d2fxyz by dx square, d2fxyz by dy square, d2fxyz by dz square. Now another are dfxyz by dx into dfxyz by dy, and then one another is required is dfxyz by dz. So I believe 6 are required. Now go and replace in the gxy. So here it is x square plus 2xy plus y square plus z square plus 2xyz plus 2yz. So 2xyz, 2yz and 2xy. So x square, y square and z square will be replaced by d2fxyz by dx square into x by factorial of 2, d2fxyz by dy square into y square by factorial of 2 plus dfxyz by dz square into z divided by factorial of 2. Now 2xy will become here dfxyz by dx into dfxyz by z into dy 2xz will become dfxz by dx dfxz by dx into dfxyz by dz. To yz will become dfxy by dy into dfxyz by dz. This is the equivalent. Now keep on x plus y plus z to the power 3. That is x plus y plus z, x plus y in bracket plus z to the power 3. Now calculate this and accordingly you proceed. So this is multivariable Taylor series when we have more than two variable also. 3. Go for with 4, 5, 6. Keep doing like this, and this is the multivariable Taylor series expansion. Okay. Now we will close the Taylor series expansion. Now we will jump into where it is useful. We have already talked about Maclaurin series. Sometime later we will talk it again. What is the use of Taylor series? Use are infinite, not one. Now consider that I have xy plane. If I have a xy plane, xy plane, consider this is xy plane. If this is xy plane, this is xy plane. If this is xy plane, this is 3D surface. If this is 3D surface, okay, then this is 3D model. So this surface is fxy, that is z, fxy. So, so consider this is xy plane and there is a surface. At each x comma y, we have z. At each x comma y, we have z. If we have z, if I connect all the z point, then it becomes a surface. If it becomes a surface, then this surface fxy, what is directional derivative? What is dfxy by dx? That is directional derivative of this surface along x-axis. What is dfxy by dy? Directional derivative of fxy along y-axis. If there is a artificial, if there is an imaginary, if this is x-axis, this is y-axis, this is z-axis, that is fxy, there is an imaginary axis called u vector, u unit vector or u vector. This is x-axis I vector, this is y-axis and j vector, then there is a unit vector u. If I say dfxy by dx is partial derivative of fxy along x-axis or I vector, I unit vector, dfxy by dy is partial derivative of fx along unit vector j or y-axis. What is dfxy by du? What is the partial derivative of fxy along any unit vector of u? If it is u vector, then unit vector of u. What is dfxy by du? If this is unit vector u, okay, then through the first principle, if I trying to calculate that dfxy by du, then any point u I have to find. From there is a delta u distance along the line only. So if it is u, then this is delta f u plus delta u. If it is u, then it is u plus delta u. At u, what is fxy? What is d? What is fu? At u plus delta u, what is fu plus delta u? If I subtract this fu plus delta u minus fu, and then I subtract it, that is delta u. So dfxy by dx, what is partial derivative? Partial derivative means along x-axis. If 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 there is unit change along x-axis, then how many unit of change I see in fxy, that is dfxy by dx, same as dfxy by dy. Now same as dfxy by du. If there is a unit change along u axis, then how many of unit change is seen in fxy, dfxy by du? If that is the case, then that is nothing but that is fu plus delta u minus fu divided by delta u. That is one unit of change along u vector. gives me gives me the dfxy by du unit of change. If that is the case, then what is the directional derivative of function fxy along u vector? Okay, very easy. Now, if I know u vector is nothing but a straight line, u vector is nothing but a straight line. fxy is function over x and y. U vector straight line, then it will come in function of x and y only. So if I take any 2 point, one is x0, y0, and I take another point x1, y1. Now I have on u vector. Understandable, right? So if this is x-axis, this is y-axis, this is u-axis, new x-axis, u-axis, y-axis. Along u-axis, I take a point called x0, y0. I take near about another point x1, y1. Now at x0, y0, what is fx? That is, what is fx0, y0? At x1, y1, what is fx1, y1? So fx1, y1 minus fx0, y0 divided by x1 minus x0 whole square plus y1 minus y0 whole square root. That is the distance. That is nothing but dfxy by du, where at point u, that is x0, y0, or in between x0, y0 and x1, y1, whatever comes to your mind. So this way we can calculate dfxy by du, but every point we have to calculate. Okay, we are in the world of algebra, then we want into term of x and y. If it is algebra, it should be in term of x and y. Not every point we go and calculate. That is fu plus delta u minus fu divided by delta u. This is not possible in term of x and y. Go and calculate. Not possible. You can break it, but you will break. So it is only possible when we go with the Taylor polynomial approximation. We'll proceed on this. So Taylor polynomial approximation. So consider this is big guava. So anyway, consider that consider this is a 3D model. If this is 3D model at any point, if I consider this is fxy, this is xy plane, this is xy plane, and this is fxy. If this is xy plane and this is fxy, then it fxy is very complex. Consider, they look like very complex, right? See, it is not even full sphere, it is very complex. So fxy is very complex. Now there is a point on xy plane, there is a point called a comma b. For a comma b, there is a point here, that is f a comma b. If it is f a comma b, for fxy I have gxy as Taylor approximation. Let's consider first order, second order, third order, just remove it, only first order. First order is dfxy by dx into x plus dfxy by dy into y, or in calculus term we can say f and down subscript, I believe, down superscript subscript. So f down subscript x, fx means dfxy by dx. So fx partial derivative, fx into x plus fy into y. This is the single order Taylor approximation. If it is single order Taylor, this is pure gxy equal to fx x plus fyy. This is pure equation of a surface, 3D surface, not this much complex. If I have a point here a comma b, at this point, if I do surface approximation, then this will become exact tangent at that point. exact tangent at that point. So at a comma b, that is FAB is exactly equal to GAB, because if it is tangent but it touches at that point, can you see it is touching that point? Where it is touching, at that point the Taylor approximation, and so gxy and fxy at that point they are same, but otherwise there is a gap. Can you see? Otherwise there is a gap. Oh, how I can show? Okay, there is a gap. One point they are same, otherwise the sphere is making round, where flat surface is going flat. There is error, but at that point it is same. So Taylor approximation is nothing but tangential surface at any point. If that is the case, then at a comma b both are same. Consider that now that is a big hint. So how we can calculate what we are trying to do? dfxy by du, dfxy by du, directional derivative of function fxy along any vector u, dfxy by du equal to fu plus delta u minus fu divided by delta u. Fu plus delta u minus fu is nothing but we are trying to calculate the delta z only, right? Dz by dfxy by du is nothing but dz by du. This is what we are trying to calculate if z equal to fxy. So if this is xy plane and this is unit vector u, along this we are trying to calculate, and on unit vector u there is one point called u and another point u plus delta u. That at u it is fu, and at u plus delta u it is fu plus delta u. Fu plus delta u minus fu is delta z. Delta z by delta u. This is what we are trying to do. So at point u, consider u Cartesian coordinate for u at point any u is a comma b. If it is a comma b, if it is a comma b, then at a comma b, now we have 3D surface, that is fxy. I have 3D surface, that is fxy, and this line is u vector. This line is u vector. I am trying to calculate dfxy by du. If that is true, then delta z by delta u. Now at point a comma, I have taken any point u on the u vector, any point u, that is a comma b. At u it is f u v. At u x comma y is fu. At any point u, that is a comma b, that is fu. So fu plus delta u minus fu, that is delta z, or fa, or we can say fa plus delta x, fa plus delta ux plus comma b plus delta uy minus fa comma b divided by delta u. This is what we are trying to say. Delta ux is nothing but, if there is a delta u distance we have taken, is x component is delta ux, or y component is delta uy. So if I say fu plus delta u minus fu divided by delta u, that is f a plus delta ux comma b plus delta uy minus fa comma b divided by delta u, where we are trying to calculate the partial derivative at point u, that is a comma b. But numerator is nothing but delta z only. That's it. So z, if I go with, if I take any point a comma b, at that point we are trying to calculate the partial derivative, that point it is same as at that point what we have single order Taylor surface approximation, because that point it is touching, it is same equation, that is z equal to dfxy by dx into x plus dfxy by dy into y. If z equal to that, what is delta z? Delta z equal to dfxy by dx delta x plus dfxy by dy delta y. So, or in other term, fx delta x plus fy delta y. Delta z equal to fx delta x plus fy delta y. If that is the case, now I can replace dfxy by du equal to delta z by delta u. Delta z is nothing but fx delta x plus fy delta y divided by delta u. Delta x, fx into delta x. What is delta x? That is, we talked about delta ux, and fy delta y. Delta x means the u. I have, if this is u vector, I have taken any point u, and from u delta u distance, I have taken another point u plus delta u. If there is a distance of delta u, then this has x component as delta ux, and it has y component. For delta u, the x component is delta ux and y component is delta uy. If I see Taylor series of first order, then it is delta z equal to dfxy by dx delta x plus dfxy by dy delta y. Delta x at point a comma b, at a comma b, delta x is delta ux and delta y is delta uy. Now dfxy by dy, this is directional derivative along u vector u. This is what we are trying to calculate, is delta z by delta u. Delta z becomes fx into delta ux plus fy into delta uy divided by delta u. If that is the case, then fx into delta ux by delta u plus fy into fy means dfxy by dy, fy into delta ux by delta u, where fx and fy are calculated at point a comma b. If that is the case, then delta ux by delta u is unit vector. It becomes delta ux component of any unit vector, because we are dividing by the magnitude. Delta uy by delta u is delta y component of any unit vector u. If that is the case, then it is fx into delta ux. If I say unit vector's x component plus fy plus delta unit y component of unit vector u, because it is delta uy divided by delta u. If that is the case, this looks like multiplication of two. It is like a dot product of two vectors. One vector is fxi plus fyj. Another vector is ux, that is unit vector x component of unit vector uxi plus uyj. If I do dot product of these two, it becomes fxux plus fyuy. So if you have a vector u, calculate the unit vector, and whatever is the x component, that is ux, and whatever is the y component, consider u vector is I plus j. Then unit vector is I by square root of 2i, 1 plus 1 by square root of 2i plus 1 by square root of 2j. Then x component is 1 by square root of 2 and y component is 1 by square root of 2. Now along x plus I, if I am trying to calculate dfxy by du, then it will become dfxy by dx at point, any point. If I am calculating x equal to a, then dfxy by dfxy by dx at point x equal to a into unit vector x component of unit vector of u, that is 1 by square root of 2 plus dfxy by dy into y component of unit vector of u, that is 1 by square root of 2 again. So partial derivative of any vector, any 3D surface, fxy dfxy by du is nothing but gradient fx and fy, dfxy by dx and partial derivative dfxy by dy, fxi plus fyj is called gradient vector of any surface. So fxi plus fyj dot uxi plus uyj, these two dot product is nothing but partial derivative of any function along any vector u. So I believe we have talked about it. We will see another advantage of Taylor series. Taylor series advantage is infinite, because you are simplifying full-fledged fxy in some polynomial equation. So first order simplification we saw. that becomes tangential surface. Second order, we will see what is the advantage. You can have n number of advantage. So we will talk about it.